Got it. Shut that down. Checking you guys here. Okay, I'm gonna go with it. Yeah, that's what I need to see. And then let me share my screen. Okay. All right. So again, like I said, I'll check attendance again around the 15-minute mark, and we're not gonna. We're here. We need to honor the time, so we're gonna go with this. I am looking for my confirmation, but I'll give it some time, and we'll go with it. Let's see. So I was checking the schedule. Basically, we need to, to kind of be on track. The goal is to do like 2 sections a day. I do not intend to rush during these sessions. I'd rather keep a steady pace. But again, anything that I intend to say live is already available in my pre-recorded sessions, right? So it's really designed for you to watch those on your own, take notes as if you're in class. What I'm doing here is just as a courtesy. But again, anything that I would say here is already recorded in my lectures and my recordings. So I would encourage you to watch those, take notes as if you're in class, just to stay on track. It's not a good idea to be behind. It is a good idea to be ahead, right? And I know last time there was students were concerned about taking 10% of 10% of your overall grade, which is 1% of your overall grade. It's not gonna, it's not. And like in all honesty, if you guys came to the end of the semester and that 10% of that homework was the difference between you passing or failing or one letter grade or another, I would just give it to you. Like I'm not gonna let something like 1% of 10% of 10% stop anybody. Right. So when I said, hey, that's not gonna hurt you, I mean it's not gonna hurt you. The main thing is be practicing, and like we're trying to get this through this content, right? Okay, so that's the long and short of all of that. Again, I'll take attendance again in about 11 minutes. So we are continuing with chapter 1. So we're going to start today with section 1.5. I think it's Leibniz notation and the power and sum difference rules, right? So we're going to, it always does this. I don't know why it does that right here. Yeah. So let's see. So we have these objectives. Let's see, some objectives here. We like to differentiate. So differentiate using power or the sum difference rule. We like to differentiate a constant or a constant times a function, determine points at which a tangent line has a specific slope. So I want to say in this section is where we're going to start to explore some of those shortcuts that I talked about. So I know last time we looked at the limit definition of derivative. Again, derivative being the slope of the tangent line at a point, and we use the limit definition to get the best approximation that we can. So when you actually find derivative, we don't usually do it that way. That stuff, what we did last time was more so for context, and so where these shortcuts and properties are coming from. But usually when we do derivatives, when you're given an equation and you can take the derivative, it's like in an instant, right? Some of the techniques that we have, right? So let's dive into it and see what it's looking like. Again, I'll check it. I know there's probably some people in the waiting room. I do my first wave at 6. Once I'm done there, I come back again at the 15-minute mark, right? So if you don't want to fall into that second wave, you definitely want to be in the waiting room at least like 5 minutes ahead of time. Just zen out. Leibniz notation, where when y is a function of x, we will also designate the derivative as f prime, right? As dy by dx, which is read the derivative of y with respect to x, right? So what this is, that limit definition, this is how we abbreviate it. Again, this guy is read the derivative of y with respect to x, okay? The derivative of y with respect to x, okay? So for any real number k, the derivative of y with respect to x of a power function, so this is going to be the power rule. Basically, when you take the derivative of a power, that power comes down and you subtract 1 from the power. That's the shortcut. So instead of saying the limit as h tends to 0 of the difference quotient, instead of doing all of that, we have this property. So when we take the derivative of a power function, all that happens is that power comes down and we subtract 1 from the power. That's the first theorem that we have, okay? Example 1, so we're asked to differentiate each of the following, okay? So now you can confirm this shortcut that we're going to do by doing the limit definition like we did last time, but let's see the shortcut or the theorem in action. So if we wanted to find the derivative, we'll notate it as dy by dx. Power rule, the 5 comes down and you subtract 1 from the power. So the derivative of that guy is this. Last time it would have been this whole limit definition of the difference quotient. The limit as h tends to 0 of the difference quotient, and it was this whole long drawn out thing. Now all that condenses into this, all right? This is the first property that we're going to introduce. So we get this result. So you see how you look at it, you do that one property and you're good to go. Okay. Let's copy. Okay. So dy by dx here. The power on x is a 1, so that 1 comes down, right? Then you have x to the power of 0. Let me think about that. Yeah. So then x to the power of 0, in this case, that derivative is just going to be 1. Paste. You know, and like since, you know, we're still a little bit fresh in my style, but, you know, I kind of wait for that 15-minute mark again, because otherwise what I experienced in the past was that every 30 seconds students would trickle in and it was like very disruptive and it would really like eat up a lot of time. So I was like, okay, I'll do my first wave at 6. We'll do that wave and then I'll check attendance again at the 15-minute mark. And then after that 15-minute mark, you're lucky if I check attendance at all, like, because we're really supposed to be in here before 6. Here, same thing, right? So power rule. So if we're going to find dy by dx, or the derivative of y with respect to x, the 4 comes down, and if you subtract 1 from the power, it becomes -5. Okay. So we're going to go like this. I'm watching the clock. I'll give it a few more minutes. So we got 5x to the 4, 1, and -4x to the -5th. And you see it here. 5x to the 4, 1, and you see it worked out here, and then -4x to the -5. All right. Okay, so that was the power rule, right? It's real short, quick, easy, simple, instead of doing that long, drawn out difference quotient. Quick check, I usually leave those as an exercise for you. Okay, so I'm just gonna kind of leave that in the interest of time. And let's give this one a go, right? So another application of the power rule. So then we have y equals the square root of x. So if we're still applying the power rule, then let's write this as a power, right? So then the derivative of y with respect to x is gonna be, another way we write it, we're gonna say d by dx. That just means the derivative with respect to x of x to the power of 1/2, right? So the square root of x is the same as x to the power of 1/2. So now, again, this notation here just means take the derivative with respect to x. So then, in other words, just take the derivative or just apply the power rule. So then dy by dx ends up being the 1/2 comes down, x to the power of a -1/2, right? Let's go a little bit further. A -1/2, I mean, we could rationalize, but a negative exponent means it drops to the denominator. I'm actually going to leave it like this for right now, but we can take that a little bit further. I will just see what the type notes say. If you're on an exam or something like that, if it's homework, you get unlimited attempts, right? Until you get it right. On the exam, say you submitted, well, the instructions are usually pretty clear about how they want the final result. Like, you know, it'll say include radicals. Like if it says include radicals, we need to take this further. So for right now, we'll just kind of go with it. But, you know, we can always kind of go back and forth and debate if you feel like you are owed some points on an exam or something like that. So here, if we take the derivative, so then our dy by dx, let me see. So if we take the derivative, the power comes down, And if you subtract 1, it's going to be x to the negative 0.3. 10th root. I'm tempted to leave it like that for right now. Let me see. We could convert it to like a fraction, and we could take it a little bit further, but for right now, I'm just going to leave it like this, and we'll see what the prepared notes say as far as the final notation for these examples, because they might go a little further, right? You see it here. So we stopped here for this one, and then again, like a negative exponent, it moves to the denominator, and then the half is really square root, right? So we should have gone a little further, right? But it's okay. And then here, see, they ended up leaving it there, right? But it's the same property. The power came down and we subtracted 1. We're good to go. I'll give it like another 3 minutes, and then I'll check attendance. I'll check for people coming late. The derivative of a constant function is 0, right? If you think about a constant is the same as x to the power of 0. So then when you go to use the power rule, that 0 comes down. Let me think about it. Yeah, we're good. Yeah, I was thinking of something else, right? So a constant is the same as that number times x to the power of 0, right? So then when you take the derivative using the power rule, that 0 comes down and basically wipes everything out, right? So then, again, long story short, the derivative of a constant is 0. So that's theorem number 4. That's another shortcut that we have, right? So we saw the power rule, the power comes down, you subtract 1 from the power. The derivative of a constant is 0. Like, I feel like, man, should I go back over this? Because this is not something that, should be missed. Now, can you guys see? Constant is 0. So that's theorem number 4. That's another shortcut. Right? So we saw the power rule. Is my image not being pushed? Because that's going through. Can you guys see what I'm writing? I feel like my image is not being pushed. Let me hop over to Zoom. Let me see the time. Because I'm not seeing it here. Let me click optimize. Let me get these guys. Let me stop sharing because I need to reboot it anyway. I think I can go here. That's fine. Let's go like this. And let's go here. Yeah, it feels like my image hasn't been shown, but that's okay. We'll get it. We'll get it going. All right. So then let's get these guys. HJK. 1, 2, 3, 4. Okay. I think I got all these guys. It looks good. Okay, cool. Let them in. Let's make this, let's close this. We want this to be full screen. All right, welcome, gentlemen. Let me check here real quick. I don't know who Farley V is. Okay, so let me kind of give a disclaimer. Screen. So just so you guys know, I know we're still kind of getting used to each other's rhythms or whatever. So with my attendance, like what I do the best I can to start right at the start of class, right? Usually I'm sitting and watching the clock as best I can. So usually what I do is I'll do my first wave. Let me check one other thing. I'll do my first wave of attendance, like right at the start as best I can. And then once I go through that first wave, I'll go ahead and start my stream. And then I don't really check attendance again until the 15-minute mark, right? So if you got in at like 6:03 or 6:04, I usually don't check it again until, like, especially, if I finish taking the attendance, then I don't check it again until 15 minutes, right? So that's what I did today. Long story short, the recommendation is to be in the waiting room anywhere from 5 to 10 minutes early, and then just kind of zen out. And I do that because my experience in the past, I would do that first wave of attendance, and then I would be doing my lecture, and then folks would trickle in like every 30 seconds. It was very disruptive, and like I would always lose my train of thought. So I was like, okay, you know what? I'll do a wave, ignore it until the 15-minute mark, and then check it again at 15 minutes. After that 15-minute mark, then it's a hit or miss whether I check attendance, because that's usually how I do that. But usually I don't make a big deal about. I mean, like if you're late, I still try to give you credit, but sometimes if it's too much, then I start not giving credit for being late. But as long as it's not like out of control, then I don't make a big deal about it. But I just wanted you guys to be aware it's a good idea to be in the waiting room at least 5 minutes before the start of class. Like that's a better plan if it can be helped. Okay, so and you missed a lot. Like I didn't realize it was going to be that much, but so and I'll do a brief recap. So we are working in section 1.5, right? And what we're doing today is we're actually starting to explore some of those shortcuts for finding derivatives that I mentioned before. Where in the previous section, when we were finding a derivative, we were doing this whole long drawn out limit as h tends to 0 of the difference quotient. Well, here we've already kind of gone through essentially 2 shortcuts, right? The first one's called the power rule, and you'll see it. It's real quick and easy. You'll catch on. But when you take the derivative of a power function, something like x squared, all we do is the power comes down and you subtract 1 from the power, right? And then this theorem number 4 is our second one that we're doing today. It's like an application of the power rule, where it's basically saying the derivative of a constant is equal to 0. If you think about a constant, like any real number, that's the same as that number times x to the power of 0. So if you have some number times x to the power of 0 and you apply the power rule, then the exponent comes down, so that 0 on the variable comes down. You subtract 1 from the exponent, and then the 0 essentially wipes everything out, right? So an application of the power rule is that the derivative of a constant is 0. In other words, the derivative of any real number. Let me think if that's okay. I feel like only one I'm kind of pausing on is 0. I had to like think about that one for a second, because sometimes kooky things happen with 0. But in general, the derivative of a constant is 0. The 0 function, actually, I want to say the derivative of 0. I want to say that's going to come up. There's something I want to say there. I'm going to let it be for right now because I don't want to misquote it. But there's something interesting that happens there. Yeah, I'm just going to kind of let it be for right now. We'll look at it. The derivative of a constant time, but I think for right now, the derivative of 0 should be 0. I can't think of anything other than that. But yeah, anyway, I think I'm overcomplicated. So this is the third property or a theorem that we have today. The derivative of a constant times a function is that constant times the derivative of a function, right? So let's look at it. Okay, so if you're just joining us, right, d by dx. Also, so I saw where somebody in the chat a moment ago asked me like, hey, can you let so-and-so in? If you're trying to get my attention, the best way to get my attention is this thing. Why does it keep? I guess I'm assuming that it's working. I guess you guys can see what I see. Let me see. So I saw where somebody in the chat. Hey, why does it keep happening? Huh. I don't think my image is being pushed because it doesn't look right. Yeah, let me reboot this thing. Let me get this student. Yeah, I don't think my image is being pushed. Are you guys there? Can you see my screen? Yeah, what I was going to say was that it's fine to like, add attention. That's going to be where you get the faster response. Can you guys see my? Okay, let me reboot this. It just, I don't know why it's doing that. Start the broadcast. It seems like it keeps like, just stop pushing my image or whatever. Like that looks good. I do that. I'll give that a moment. All right, I can see it doing that. And the only reason I'm knowing because I'm actually watching my stream as I stream, and it's like, okay, wait a minute, something's off. But yeah, for a faster response for me, the recommendation is to unmute yourself to get my attention. That way, because the chat, I just check it periodically. Okay, so with this one, right? So the derivative of a constant times the function, okay, is going to be the same as the constant times the derivative, right? So essentially, we can factor out that constant. All right, that's essentially what's going on. And again, if you're just joining us, this notation, I want to say this is Leibniz notation. This is read, basically this is saying take the derivative with respect to x of this guy. The derivative with respect to x of this is going to be the constant times the derivative with respect to x of this. Okay. All right, let's let that be for now. So for each of the following, find the derivatives, right? So we're going to see all three of the shortcuts that we kind of talked about today in action here. Again, the first one being the power rule. The derivative of a power is going to be that power times, that variable to the power. Basically, you subtract one. The power comes down, you subtract one. You'll see it. You'll see it. And it's easier seen than said, right? We got the power rule, the derivative of a constant, and the derivative of a constant times the function, right? So here, if we're taking the derivative here, we just said that we can factor, so this should be equal to 7 times the derivative of x to the 4. So that's going to be 7 times, now if we apply the power rule, that's going to be 4x to the power of 3, which is ultimately 28x cubed, right? So again, if you're just joining us last time, if we were to try to do this derivative, it would have been this long drawn out, limit as h tends to 0 of the difference quotient. Now that's how quick we can do it. So that all that page of work that we did is condensed into those 2 lines, right? That's what I mean. Like I felt like it gets easier, at least as far as the derivative is concerned, going forward. Okay, it's looking fine now here, right? Same thing here. So if we take the derivative here, the 9, you can just let me write it all the way out. So the 9 I'm kind of just pulling out, and this is going to be d by dx. This is the derivative with respect to x of x. So if we apply the power rule here, the power on x is 1. The 1 comes down, and you subtract 1 from the power. And so long story short, the d by dx of x is just 1. So long story short, this guy is just -9. Okay. Now let's do it like this. Paste. I think I do have let me see if I can get it to work. Is it this one? Oh, they almost did it. Nope. Oh, what am I doing? No. Okay, it's fine. I'll let it go. I almost did it though the first time. Anyway. And so this one is asking us to do the derivative with respect to x of this guy, right? So let's and again, if anything is not clear, may I encourage you to feel free to unmute yourself to get my attention and we can talk about it. Don't take me being irritable as anything. It's not anything. I'm just a human, right? But I don't want you to be intimidated. Like I want you to still ask questions and let your voice be heard. This is a lab, right? Like this is a place where we're here to learn and grow, Anyway, okay. So if we factor, I'm going to rewrite this guy. I feel inspired to first let me factor out that 1/5, right? So I'm just going to kind of pull that guy over here. And then what's going to be left, we're going to have the 1/x. I'm going to rewrite that 1/x as x to the power of -2, right? So then we still need to take the derivative, but instead of leaving it as 1/x squared, I'm going to rewrite it as x to the -2. Okay. All right. So now we apply the power rule where basically what we're saying, the -2 comes down and we subtract 1 from the exponent. So then that's going to give us 1/5 -2 x to the -3. Okay. So then if we kind of multiply, combine like terms and stuff like that, on bottom, it looks like we're going to have 5x cubed. On top, we're going to have 2, and the whole thing is negative. At that point, it's algebra. That last step was like algebra. Okay. Let me check on you guys in Zoom. All right, I think we got a couple more. Oh, I thought I had let him in. Let me get these students. Maybe he kind of got booted or something. There he is. Okay, let's keep going. He's not able to keep up with the screen switching. I think that's what, because this one I noticed it before. Let's just give it a moment to like boot. Let me see. So we got for A, 28x cubed. I think we got that. We got -9 there. Okay. And I think we got this guy. Okay. It looks okay. Looks good. Let me see, what's the time? So again, the goal is to get through 2 sections a day. Let me just keep moving. So sum and difference rules, right? So we've seen the power rule, we've seen the constant rule, we've seen the constant times the power. So now we're going to look at when we take the derivative of a sum, right? The derivative of a sum is going to be the sum of the derivatives. Let me do that one more time. The derivative of a sum is the same as the sum of the derivatives. All right, so it's almost like you're distributing the d by dx, but that's not really what you're doing. But you know, when you're taking the derivative of a sum, that's going to be equal to the sum of the derivatives, right? Similarly, when you take the derivative of a difference, that's going to be the difference of the derivatives, right? Okay. So hopefully this is clear. Again, if anything is not clear, feel free to unmute yourself. A closed mouth don't get fed. You got to speak up. All right. If you don't say anything, then we can't provide the necessary attention. And you know, you don't want to let things fester. Find each of the following derivatives, right? Okay, so now we're applying all the different techniques that we've kind of talked about today. So for the first one, I'm just going to kind of write the results. The 3 comes down, so that's going to be 15x. We subtract 1 from the power, that becomes 2. Minus, actually the derivative of a constant is 0. So only thing that's left is this guy. The 3 came down, you subtract 1, and then the second one, the derivative of the constant is 0, okay? So then for this one, 24x, that derivative just becomes 24. We saw an example earlier where we did square root of x, that derivative. Remember, square root is the same as x to the power of 1/2. So then when we apply the power rule, that 1/2 comes down, and we're going to have x to the negative 1/2. I'm going to leave it like that for right now. And then that last one, that 5 divided by x is the same as 5 times x to the minus 1, right? So then that minus 1 comes down, we're going to have minus 5x to the minus 2. If I need to kind of show those intermediate steps, just let me know. But again, here, I rewrote it as 5 to the 5 times x to the negative 1. Changing the form and then applying the power rule, we got this result. Oh, okay. Okay.
Professor,
Yes.
how did you get the negative 1/2
Okay.
x to the negative 1/2?
So for that one, I'm just gonna isolate that term. I'll do it like here, I guess. So undo. What did I click on? D by dx of negative square root of x. First, we rewrote that square root as a rational exponent, right? So that's going to be the same as the derivative with respect to x of negative x to the 1/2. So square root is the same as x to the power of 1/2. Then we apply the power rule, right? So when we take the derivative, the 1/2 comes down and we subtract 1 from the power. And then that's where this came from. Okay. Now, you know, the last is just like semantics. Now, we probably should rewrite this, put it back into a radical, maybe move this to the denominator. Let's go ahead and do that. I'm just gonna kind of say continue here. Okay, so then I'm just gonna go 24. This is gonna be minus, on bottom, we're gonna have 2 times the square root of x, okay? And then the last term, 5 over x squared, okay? Paste. If you're taking notes, I do officially have an office now, at least for the time being. It's Dansby 201. I'm usually in there like Monday through Thursday mornings before 8 o'clock. All right. On Tuesday and Thursday, it might be maybe before like 9. It's not official office hours. I'm just like, if you need to see me in person, I actually have a location where you can come to. All right. Dansby 201. And again, but I'm in there early, basically before my classes. Once I get out of class, then I usually go somewhere. Okay. I'm going to go with this. So what's the time? That's okay. You see, let me see. The first one, we got 15x squared, and you see it here. The second one, we got that long drawn out thing, and you see it here. They got this one. Now, again, I was tempted to stop here. When you get on the assignments, there'll be specific result to be, right? Okay. Okay, it's looking good. It looks like it's still clicking. All right, so quick check I leave as an exercise for you. Let me see. If we start at 925, 50 plus 7, let me think about it. 6 to 715, so that's 60, 75, 35, 36. It's about 40 minutes. Okay, so we got a little bit of time. Okay. So find the points on the graph at which the tangent line is horizontal. All right. So we have this function. We want to find, so what has been the whole discussion been about for this chapter so far? Where have we been talking about the tangent line? All right. The tangent line popped up because we said, it was like the very first thing that we said, and we kind of been saying it on repeat. The derivative is the slope of the tangent line at a point, right? Let me say that one more time. The derivative is the slope of the tangent line at a point. So then if they want us to find where the tangent line is horizontal, that means we want to find where the slope is, hopefully you're thinking 0, right? So long story short, they're asking us to take the derivative and set it equal to 0 and solve, right? Instead of just saying, the simple thing would be, hey, take the derivative and set it equal to 0 and solve, but that's too linear, I guess, for this, right? So we have this curve. We want to find all the points where the tangent line is horizontal. In other words, find the derivative, set it to 0 and solve, all right? Okay. So we're going to apply our theorems and our shortcuts today that we've been talking about today and go ahead and quickly find the derivative. So then our f prime, okay? So the first one, we apply the power rule that 3 comes down. Subtract 1 from the power, we get this. Same thing for the second term. The 2 comes down, so that it becomes 12, and subtract 1 from the power, we're left with the 1 there. Okay, so this is our derivative. So then, if we want to find when the tangent line is horizontal, that's when this guy is going to be equal to 0. Okay. Let's factor out a greatest common factor. It looks like both terms have a negative 3x. It looks like we can factor out negative 3x from both terms. When we do that, that's going to leave an x in the first term minus, what is that, 4? Okay. And we just check by distributing back. Okay, that looks good. Okay, I think that looks good as well, right? So then we said, now we have the 0 factor property. We have 2 or more things that multiply to give us 0. We set each thing to 0 and solve. So then from the first one, we get x equals 0 or x equals 4, right? So those are the x's. So if it wants us to find the points, then we need to find the corresponding y's. So when x is 0, so one of the points where the slope of the tangent line should be horizontal, it should be 0, is going to be the origin, because when x is 0, the corresponding y is 0. And then when x is 4, 16 times 4, here. Hey Siri, what's negative 4 cubed plus 6 times 4 squared?
Negative 4 cubed plus 6 times 4 squared is 32.
32, right? Instead of, use your calculator. When x is 4, right? So those 2 points. Now we can plot these points, look at it. We can find the equation of the tangent line. Let me see. If it has a slope of 0, so it's just going to be y. Like if we drew horizontal lines, y equals 0, basically the x-axis, and y equals 32, we can see that it would graze the curve at a flat tangent or whatever. Okay. Recall that the derivative is the slope of the tangent line to a curve, and that the slope of a horizontal line is 0. So therefore, thank you. I know we're halfway. Stop. So therefore, we wish to find all the points on the graph where the derivative of f is 0, right? So that's what we did. Okay, so we took the derivative, we got that guy, we set the derivative equal to 0, and they got 0 and 4 like we did. Okay. All right, I'm gonna do a scan because I want to kind of move on to the next section because we're about at the halfway mark. Y values. Oh, and then they're kind of wrapping up example 5, right? And so here's the pictorial representation. The curve, we have the original curve. We see that we get a flat tangent line at the origin, and when x is 4, y is 32, right? Okay. Find the points on the graph at which the tangent line has a slope of 6. This one is done in a similar fashion. You take the derivative, but instead of setting it equal to 0, you set it equal to 6 and solve, right? So I'm going to leave that one as an exercise just in the interest of time. Okay, you can see it here. It's a little bit more involved, right? I'm gonna let that one be for now. Okay. So let me take a moment to go ahead and pull up the next section. And I can check on you guys in Zoom, so just give me just a moment. Oh. Let's go here. Let me just stop the broadcast. Oh, no. Yeah, thanks. Because I was like, you don't have to have your video on. I don't know how to turn it off right now. You guys are looking good there. All right, so okay. I need that to be suppressed. So we're working on 1.6. It's right here. Let me duplicate. Okay. Yeah. Where did I put it? This one. I want it right here. And let me see what section this is. This is about 1.6 is the product and quotient rules. Okay, so the next set of shortcuts, right? All right, so this isn't too bad. Product and quotient rules. Let me just put a label. This is week 3. This is Wednesday, 6 p.m. This is 1.6 product, and let's do like this, quotient rules. That's fine. Calculus. Oh no, what happened? Calculus for business. You are like bugging. Business. Okay, that's fine. So let me do one other thing. Let me go ahead and make a copy of what we did before. Let me share. I want to send it to box. Come on. Spring calculus notes. I need to change that title. All right. So what I'm doing, I'm loading a copy of what you saw me writing for section 1.5. I'm making that available. As soon as this finishes loading, we're going to go ahead and open up 1.6. All right, so we're here, right? That looks good. Let's go right here. Let me share my screen. Start the broadcast. Boom, that looks good. We're here. Okay, cool. All right, we're gonna go with it. Move this over here. Okay, and let's do view, single page. And I think you're doing that thing again. So let's go like this. Okay. I think I had to go through the settings and disable that. I'm gonna assume that it's working. You guys can see my screen. It looks like it's clicking. Okay. So again, in the previous section, it was mostly applications of the power rule, right? This is a shortcut that we have for finding the derivative. Instead of doing that long drawn out limit as h tends to 0 of the difference quotient, you can look at it and get it, bro. We also saw the sum and difference rule, right? The derivative of a sum is going to be the sum of the derivatives. The derivative of a difference is going to be the difference of the derivatives, right? So here we're going to look at the product and quotient rules for differentiation. So the objective here, we like to differentiate using the product. Yes.
I can't see your screen.
No good. No bueno. Okay. Thank you for that. Only thing I can think to do is just stop and restart this thing. Full screen. Start the broadcast. Optimize. Let's just give it a moment to load. Can you guys see my screen now?
All I see is just a screen saying that you are sharing a screen or something.
Is it getting stuck there? I think it might need to be rebooted. It's still showing the sharing the screen.
Yeah.
Okay. Let me try rebooting this. I don't think this is the culprit. I'm trying not to reboot Zoom, but I might have to reboot Zoom. Back to the meeting. Let me stop this. Let me stop it one more time. Share my screen. Stop the broadcast. Okay. Let me reboot my Zoom. I'll be right back. Hang on. Okay, we are back. Let me share my screen again. Start the broadcast. All right. Let's minimize that. Let's go here. You guys see my screen now? The only other thing, okay, I see it there. It's trying. Can you see my screen? Like,
yes.
Okay, what does it say?
It's adjective.
Okay, cool. Okay. Yeah, sorry about that. Yeah, it's just, yeah, like the technology is temperamental. It totally is. It's, a lot of times you have to reboot stuff, but because of the nature of this structure, this is why I do unlimited attempts. I hate to say this whole late penalty thing, but 10%, it's not gonna stop you, right? As long as you show command of the material, the content, you get your stuff submitted. If you're close, I don't slight the students. I don't do that. Like, I'm like, okay. Like, I usually do not get, I don't remember the last time I've given out a C- or whatever. Usually if you're close, because I do acknowledge, the discrepancy about the 10%, but I can't, like, I think my hesitation in like doing that, the augmentation was I designed it so that it doesn't need to be tampered with. You know what I mean? Because if I make that change for that one, then every time we turn around, she was like, can I get an extension? I was like, no, I already built the extension in, right? But so, anyway, let's let all that go. But anyway, okay, so 1.6, the product and quotient rules, okay? So to kind of a quick recap, we want to differentiate using the product and quotient rules, and then use the quotient rule to differentiate the average cost, revenue, and profit functions, right? So these are some applications of the derivative. So let's look at the product rule, right? Let me see, how do I remember this? So the product rule. So say we have one function times another, and we want to take the derivative of that product. So the derivative of the product, the way I remember it is the first times the derivative of the second plus the second times the derivative of the first. Okay, let's do that one more time. The way I remember the product rule, when you're taking the derivative of a product, that's going to be the first times the derivative of the second plus the second times the derivative of the first. Okay, so that's how I remember the product rule, right? So let's see if we can see that in action. So here we ask to differentiate, right? So let's apply the product rule, right? So this is going to be equal to the first, which is going to be x to the 4 minus 2x cubed minus 7 times, I'm going to say d by dx, the derivative of the second. So I'm going to come back and take the derivative momentarily. Plus, I'm running out of space, so I'm going to drop down the line. So I said the first times the derivative of the second plus the second, which is this guy. And I'll rearrange it to put it on one line. Times the derivative, so d by dx of the first. Okay. And let me just, since I'm on a digital device, I'm just going to change the size. Shrink it down to size. Okay. Here, and then I'm going to kind of expand it back as big as I can get it. All right. Something like this, right? So we did the first times the second plus the second times the first. Now let's go ahead and take the derivatives, right? So that first part, it just comes down. Okay. So then that derivative there, we can apply like the power rule. The 2 comes down, that becomes a 6. 2 minus 1 is 1, so that's why it's just 6x. Negative 5x, that derivative is just going to be negative 5. Okay. Plus the 3x squared kind of persists. And then that derivative becomes, the 4 comes down and subtract 1 becomes 4x cubed. The 3 comes down, that becomes 6x squared. The derivative of a constant is 0. Okay. Let me see, do we have any like terms that we can factor out before we expand this guy? You know what? I think we can actually leave it here for right now. Again, as you start to work on different assignments, I'm gonna leave it here for right now. Now, if they want us to go further, we will. You know, we can expand this, obviously, combine like terms and all this stuff. But I think for right now, we can just leave it like that. And you see it here, right? We could have expanded that, but for right now, we left it. Okay. And again, when we get on like the quizzes and exams, they're very specific about, you know, how they want the result. All right. And so it does take a little bit of adjusting. That does take adjusting because of like nuances between technical difficulties and just understanding the computer. This is why I do unlimited attempts. And I try to do like the least amount of late penalty where I'm comfortable, but I don't really want to slight you guys. I can't give you full credit for like late stuff, but I don't want to I don't want to slam you guys. Quick check I usually leave as an exercise. So in interest of time, you know, we got a solid 25 minutes. We're pretty good for right now. We can come back to this, but I'm gonna leave that for you guys. All right, so we saw a demo on the product rule, right? Again, the product rule was when we take that derivative, it's gonna be the first times the derivative of the second plus the second times the derivative of the first, right? So now when we do the quotient rule, the way I remember quotient rule, I gotta go like this. Low D high minus high D low over low low, right? Let's see what do we mean by that. So when we're taking the derivative of a quotient, low, so the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Again, the way I remember that is low D high minus high D low over low low. Bottom times the derivative of the top minus the top times the derivative of bottom over bottom squared. Right? It sounds like a song. Low D high minus high D low over low low. Right? It's a little bit weird, but yeah, that's how I remember. Right? Okay. So that's the quotient rule. So here we're asked to differentiate, right? We got a derivative. So let's apply the quotient rule. Low, which is the bottom, so that's going to be this guy, we'll say f prime. So low, which is this, d high. So the derivative of top is going to be what? 2x minus 3 minus, let me see, low d high minus high, which is this guy, d low, which is just going to be a 1 in this case, all over low low, which is the bottom squared. That's the quotient rule, right? Do we have anything common that we can factor out? We have an x minus 3. Something common to cancel. We could expand it, and it's not too terribly difficult. I'm tempted to expand it, so let me see what they do. Okay, yeah, let's go ahead and expand this one. So then here, if we FOIL, that's the first part. 2x, let me see, first is 2x squared, outer is minus 3x, inner minus 2x, and last is plus 3. Distribute that negative, we get a negative x squared plus 3x. And I'm going to keep my low. Okay. Then combine like terms. Let me see. So we got the x squared. Okay. Minus 3 minus 2 is minus 5. So I think those 3's cancel. Let me show it here. This guy is going to be canceled by this one. So it looks like we're left with minus 2x plus 3 over x minus 1 squared. Okay, hopefully that's okay. I think you're starting to catch the rhythm on, how to get my attention. Okay, we're going to go with that. We got this x squared minus 2x plus 3 over x minus 1 squared. And you see a type version of what we just did, right? Okay. All right. Okay, we're actually on track, right? We're not that far behind, right? We're actually almost done with this section. Quick check, I leave as an exercise. Okay. Let's look at this definition. Let's talk about this. So if C of X is going to be the cost of producing X items, right? So we have this business, and this is going to tell us how much it costs to produce however many items we want. Then the average cost of producing X items is going to be given by this. When you think about average, right? Like if you were calculating your average in a class, like your exam average, then you would add up all your exams divided by the number of exams. So then here, if we want the average cost, it's the total cost divided by the number of units produced, right? So the total divided by the number of units. Similarly, if R of X is going to be the revenue from the sale of X items, then the average revenue from selling X items is going to be the total revenue divided by number of items, X. All right, so however many items we sold. And lastly, P of X is going to be the profit from the sale of X items, then the average profit for selling X items, P of X over X, right? So average cost, revenue, and profit, which is the total cost, revenue, or profit divided by X, okay? All right. So then Paulseen's greenhouse, find that the cost in dollars of growing X hundred geraniums is given by this cost function. If the revenue from the sale of X hundred geraniums is given by this cost function, then find each of the following. We're asked to find the average cost, the average revenue, and then the average profit when X hundreds of geraniums are sold, right? And then we're also asked to find the rate at which the average profit is changing when 300 geraniums are being grown, right? So rate, I don't know what that is. They're gonna have to leave a message. Rate is basically what? Slope or derivative, okay, in this context. Okay. Let's see. We got our costs, we got our revenue. Okay. Let me add a page. Let me go view seamless. And right here, I want to add a page. Let's add another page. Okay. All right. So let me start by getting a copy of our cost function. That's 200. Come on. That's 200 plus 100 times the fourth root of X. Okay. And then our revenue function, we're given it as 120 plus 90 times the square root of x. Okay. So they want average cost. Okay, so we're going to abbreviate. So then for A, average cost, we're going to abbreviate it like this. That's going to be our total cost. And let me do it like this. That's going to be our total cost over the number of units produced. All right. Okay. Come on. That's fine. So then that's going to be, I guess we can just leave it as 200 plus 100 times the fourth root of x all over x. We're just going to leave it like that. Okay. And then it's yeah, because it doesn't like it really simplifies or anything like that. So then the average revenue should be R of x over x. Let me make that look more like an R. So then that should be 120 plus 90 over the square root of x. 90 times the square root of x over x. Okay. Yeah, we're just going to go with it for now. And then the average profit. That should be the total profit divided by x. So profit in business is what? Revenue minus the cost, money generated minus money spent, money in minus money out. So it's going to be our revenue. The profit function is going to be our revenue function minus our cost function, right? So the total profit, let me see, the average profit is going to be 120 plus 90 times the square root of x. That's the revenue minus the cost. So we need to distribute that negative minus 100 times the fourth root of x, okay? All over x. Okay, now we can simplify that one a little bit. We can combine like terms. It looks like it's really just the first one. What is that, a negative 80? Negative 80 plus 90 times the square root of x minus 100 times the fourth root of x. Okay, all over x. Okay, so let's highlight these. So we got this guy, we got this guy, and we got this guy. Okay, so then they asked us to find the rate at which the average profit is changing. Profit when 300 geraniums. Wait a minute. The rate at which the average profit is changing when 300 geraniums are being grown, right? This cost, revenue, and function are in terms of hundreds of geraniums. So in this case, it looks like X needs to be 3. I was about to put 300 in there, but then I was like, wait a minute, we got to make sure we're matching up. Again, these were created, we got a solid 10 minutes with in terms of hundreds of geraniums. So we have 300 geraniums. So I'm going to let X be 3. Okay. And it wants the average rate. It wants the rate at which the average profit is changing. So in other words, d by dx, right, of the average profit. All right, let's give that a go. So then for B, if we take our average profit, we basically want to take the derivative. Okay. Let me write it. And let me put of 3, right? When X is 3. Okay, so we could use the quotient rule, right? Because we do have a fraction. We could also rewrite that X. We can, I think I'd rather not use the quotient rule because that's going to be a lot. It's going to make it worse, I think. I'm going to rewrite this where I move the X up. I'm going to distribute the X into those 3 terms and then then take the derivative, right? So what I'm saying is I want to do d by dx of, now I want to move the x up. So it's going to become negative 80 x to the negative 1. Let me make that look a little bit better. Let me think about that. If you have x to the 1/2, so it's going to be 1/2 minus 1. That's ultimately going to be plus 90 times x to the negative 1/2, right? I did x to the one. I did 1/2 minus 1 to give me a negative 1/2. Okay, and then in that last one, you got 1/4 minus 1 to give us a negative 3/4, right? So 100 x to the negative 3/4, right? Here, this is x to the 1/2. This guy is x to the 1/4, right? So then when you say one fraction divided by another, you subtract the exponents, okay? All right, we're almost there. So now let's go ahead and take our derivative, okay? So then for the first term, the negative 1 comes down. We get our 80. If you subtract 1, it's going to be x to the minus 2. Okay, the next one, the negative 1/2 comes down. That's going to give us a negative 45. And if you subtract 1, it's going to be a negative 3/2. Okay. The final one, the negative 3/4 comes down. That becomes positive. That's going to be 25 times 3 is 75. And if you subtract 1, negative 7/4. Okay. And we need to evaluate this when x is 3. Okay. I think I'm going to use a calculator for the remaining part, right? I'm going to write it out here. Did I make a mistake? You see something wrong?
Where did you get the negative 80x to the negative power from?
You talking about this guy here? Negative 80x to the minus 1?
Yes.
I'm not sure. Let me finish. Oh, okay. But right here. So when I wanted to take the derivative of the thing at the top of the screen, I rewrote it where I moved this x up because I'm dividing by a monomial. We can distribute it across the top. But and so I did that by rewriting the x as x to the minus 1. Right, and here, this is a 1/2 divided x to the 1/2 divided by x to the 1 is x to the minus 1/2. X to the 1/4 divided by x to the 1 is x to the negative 3/4. Let me check and make sure this is correct, and we can talk about it some more. So then we're just about there. So then we're gonna let x be 3. 80 times 3 to the negative 2 minus 45 times 3 to the negative 3/2 plus 75 times 3 to the negative 7/4. Okay, so I'm just going to crunch that number. So what I'm going to do is break out my trusty dusty rusty. We want a new tab. Okay, that looks good. Like this. I think this is fine. I can work with this. Okay. So again, this is what I mean by like, you got to be neat and organized, kind of take your time, space it out, write big, because it's very easy to lose track of some of this stuff, right? Let's see. So I'm just going to type in 80 times 3 to the power of negative 2. Okay, using my parentheses. We're going to say minus 45 times, that's not a 45. And I did that wrong. Okay. 3 to the power of a negative 3/2. Okay. Plus 75 times 3 to the power of negative 7/4, right? So we're going to cross our fingers. Hopefully we didn't make any mistakes and we're okay. Okay. Drum roll. Okay. So let me see. It says the average rate, cost, profit. Is that the rate at which the profit is changing? $11.20. Is that right? Let me see. So we got 11.20. Let's see, how do we do? All right. Approximately, I think it's $11.20 per geranium. I'm going to say per geranium. Per 100 geranium? I'm a little bit missing the units here. Geranium. I'm going to abbreviate it right now. Let's see how do we do, and we'll try to get to the bottom if we didn't get it right. Okay. Let's see. Let me get rid of this extra page. Delete that, and let's go view single page. Okay. All right. So we got this result. Oh, I should have did that earlier. That would have been nice, but that's okay. This is fine. Oof. Okay. Actually, I'm gonna do something. Give me just a moment. Give me just a moment. View, single page, seamless. I want to go here. I see the time, templates. This one's what I want. Apply. That's fine. Yeah, that's okay. I have to fix that. Where'd it go? Did I lose my page? Just quick check. Okay. Hang on. I can get it right here. All of this. Let's cut. Okay. And I think it's here. Let's paste. And then what we need to do is kind of like this. That's fine. Right. I basically was just reformatting it so the pages have the same shape, one of them to be landscape and the others were, portrait or whatever. Or all of these are landscape and one was portrait. So I was just trying to get them the same. Okay. So here's the work that we did, right, with our result. We got 1120. Okay, let's see what did the text do. All right. So we let AC, AR, and AP average cost, revenue, and profit. All right. You see it here. I think we got all these results. We got all of this. All right. Okay, we're good there. So then we had to find the derivative, right, with respect to x. I feel like we were missing something. 100 x squared. Okay, they used the quotient rule. That's fine. They got some like terms to combine. I think we might be the same. Do we have that 100? We had 75. Let's see. I think we might have missed something. We might have to go back. 4. Nope. 75. We're good. Yeah, I think we got it. I'm optimistic. Yeah. Bingo! You gotta celebrate these little micro successes. The more you celebrate those micro successes, they expand, right? If we complain all the time, that expands too. The thing that we don't realize that as humans, whatever we focus on and whatever we practice and think about day in and day out, it expands. You see what I'm saying? So when I make these little successes, I have a mini party. This is fun. So at 300 geraniums, the average profit is increasing by $11.20 per plant, right? Per geranium. That's what we were saying. Okay, cool. And we were right on time, right? So this is a recap. So the product rule, right? The way I remember product rule is first times the derivative of the second plus the second times the derivative of the first. You see it all written out here. And then the quotient rule, low D high minus high D low over low low. All right, that's how I remember the quotient rule. You see it all written out here. Okay. And again, so the name of the game with a lot of these, you got to take your time, be confident, be neat and organized as possible. Space it out, give yourself plenty of space. Minimize your distractions, like because if you write too small or too cluttered, you got too many distractions. It's very easy to lose track of your work, right? And then it's such a pain when you get to the end, you get a result and it's wrong. Now you got to go back and try to find where did you make your mistake, what are you missing, and so you it's very meticulous and tedious, right? But it's neither here nor there. Okay. Did you guys have any questions? Would you like to ask any questions? Let me while you think about that, I'm going to go ahead and make a copy of this available right there. That looks good. I'm gonna send it a box. So when this bar finishes loading, anything that you saw me writing today, you'll have a copy of it available on Blackboard. All right. So with the completion of this section, I think we only have 2 more sections to complete in chapter 1. We will get caught up. Again, I don't want to rush. I just want to kind of keep going at my rhythm. So we're not that far behind. but continue to, use my YouTube. It is a good idea to be subscribed to my YouTube with the notifications turned on. So as I start replying to like the Ask My Instructor and you guys questions, you can at least be aware that I've created a video response. You don't necessarily have to watch it, but it is a good idea to be aware. Also, you want to definitely, I still want to encourage you to watch my pre-recorded lectures, take notes as if you're in class, because basically the stuff that's in those recordings is the exact same thing I would say live, right? So, do your best to stay on track. If not, get ahead. And if are there any burning questions before we end? Going once, going twice. Okay.
Professor,
Yes.
for the last problem, when did we substitute 3 for x?
3 for x. That was at the end, right? So we got our average profit, which you see that last purple line there. Okay. And then, then we had to find the rate of change of the profit for 300 geraniums. So when it said the rate of change, that means we needed to find the derivative. So we rewrote it, where we moved the this guy to the numerator. You see it here, and we had to do some simplifying, right? And then after we did that, then we took the derivative. So the power came down. That's why that became positive. This one came down. You see it here. You subtract 1. This one comes down. You subtract 1. You see it here. Okay. So this line was after we took the derivative. Then once we took the derivative, it wanted to. The rate of change of the average all of this was built in terms of how we did 3 for x. So then we plugged in our 3. Take your time. Go ahead. And like, I mean, okay, I'm willing to extend the following. When I leave you guys here, I'm not going to be doing anything, but I might eat, sleep, or game, or watch something on YouTube or something like that. So I say that to say, if anybody wanted to stick around and go through homework questions, I'm game. Otherwise, we'll stop here and we'll reconnect back on next Monday. Okay. All right. That was a good. Any other burning questions before we go our separate ways? Okay. So I think our first exam isn't until week 6, so we still got a good amount of time. Oh my goodness, why won't you go to that last page? Okay, so if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great weekend, guys. Work hard, play hard, and enjoy your life. All right, take care. Peace. All right, gentlemen.